All right, we're looking at the back page of the Chapter 1 Limits Review Worksheet. It says refer to the graph to evaluate the following limits. So limit as x approaches -4 from the right side of -4. So here's -4. We're approaching -4 from the right side of -4. We're doing one side limit. We're just concerned about this right branch here. And we see the graph is going down to -infinity. As we approach -4 from the left side of -4, we're concerned about this branch here. So from the left side of -4, we're approaching -4, and we see the y value is shooting up to positive infinity. Okay. As we approach positive infinity, that means we're going to follow the graph off. We're going to follow the graph to the right, and if we follow the graph to the right, off the graph, we see that it's leveling off at a y value of 5, horizontal asymptote at 5. As we approach -infinity, so we're going to follow the left branch here, we're going to go off the graph, and we see the graph is leveling off at also y equals 5. Okay, 146 here. As we approach A from the right side of A, so here's A. From the right side of A, we're following the right branch, is going up to positive infinity. As we approach A from the left side of A, so here's A, from the left side of A, we're going towards A. From the left side of A, we see the graph is going down to -infinity. Limit as x approaches 0, so as we approach 0, so that's the y-axis, we see the graph is going to be continuous through that point. So that means we can simply look at the order pair. So the order pair is going to match the limit because this is a smooth continuous graph. So the y value at 0 at this point is d. Okay. Remember, with limit, we're always trying to provide information regarding the y value. As we approach positive infinity, so if we approach positive infinity, we're going to follow the graph off the graph, and we see the graph is leveling off at this dotted line. That dotted line is that y value of c. As we approach B from the right side of B, so here's B, from the right side of B, we're following this right branch towards B, and we see the graph is shooting up to positive infinity. Okay, refer to the graph, determine whether each statement is true or false, and if false, explain why. Alright, so we have a graph f of x here. There's a hole, and then order pair at 0, 1, order pair at 1, 0, and order pair at 2, 0. So limit as x approaches -1 from the right side of 1 is equal to 1. Okay, so as we approach -1 from the right side of -1, we're talking about this branch, it's actually going to go up to positive 1, so that's true. 153. As we approach 0 from the left side of 0, so here's 0, from the left side of 0, we're following this branch in this direction, it's equal to 0, and that's true. Okay, when we're evaluating one side limit, we're looking to see where the graph is connecting to, and whatever happens at that point is beside is not the issue. The issue is where the graph is leading towards. So even though the order pair exists at 0, 1, the limit exists at y value of 0. As we approach 0 from the left side of 0 is equal to 1. We know that's false because it should be 0. 155, approaching 0 from the left side of 0 is equal to 0 from the right side of 0. So as we approach 0 from the left side of 0, it's going towards the origin. From the right side of 0 is also going to the origin. So we know that is true. Limit as x approaches 0 does exist, and it's equal to 0. Limit as x approaches 0 is equal to 0. We know that's true. And then limit as x approaches 0 is equal to 1. That's false, because the limit as we approach 0 from both sides of 0 is approaching this hole and is not approaching that order point, that order pair. So false. Okay, limit as x approaches 1 is equal to 1. So as we approach 1, we see that it's approaching 1 on the left side, but there's nothing on the right side. So therefore, in order for a limit to exist, the graph has to exist on both sides of that x value. Okay, so false. So there's nothing on the right side of 1. All right, limit as x approaches 1 is equal to 0. As it approaches 1, we see that's false because the limit does not exist. Limit as x approaches 2, from the left side of 2, there's nothing, there's no graph on either side of 2, so limit does not exist. Limit as x approaches negative 1, from the left side of negative 1, the graph, there's nothing on the left side of negative 1, so does not exist. That's a true statement. As we approach 2, from the right side of 2, there's nothing on either side of 2, so false. So even though the order pair exists at 0, at 2, 0, there's no graph, nothing to connect, so limit does not exist. All right, bottom of the page here, find the value of the following limit if it exists. So at limit as x approaches 9, the first thing we do is we plug in the x value of 9, and we get 3 minus 3, which is root 9, which is 3. So 3 minus 3 is 0, 9 minus 9 is 0, 0 over 0, which means that we can do something further to evaluate the limit. And this is actually going to end up being a conjugate problem. So we multiply top and bottom by the conjugate of the numerator. So the conjugate numerator is 3 plus root x. We distribute through, we get 9 minus x. And then we see the factor of 9 minus x cancels out. We reevaluate the limit. There's a 1 left over at the top of the expression here. So plug in 9 in for root x. Root 9 is 3. 3 plus 3 is 6, so 1/6. Okay, 17. If we plug in negative 2 to begin with, we get 0 over 0. So that tells us we can keep going with the problem by factoring. So numerator factors to be x plus 2 times x plus 3. Denominator factors to be x plus 2, x minus 2, difference of squares. So we can cancel out the x plus 2's and we reevaluate the expression. We get negative 2 plus 3, which is 1. Negative 2 minus 2 is negative 4, so negative 1/4. Okay, first thing we do is we plug in 4 into the expression. So plug 4 in for x. We get 16 minus 12, which is 4. 4 plus 4 is 8. 4 in for x, we get 16 times 2, which is 32. 32 minus 4 is 28, minus 1, 27. So we're left with cube root of 28 over 27. Cube root of 8 is 2. Cube root of 27 is 3. So therefore, our limit is 2/3. All right, 19, first thing we do, plug in the 2. 2 in for x. 2 in for x, we get 4 times 2, which is 8. 8 plus 3 is 11. 2 in for x, we get 2 times 3 is 6. 6 minus 6 is 0. 11 over 0 does not exist, so limit doesn't exist. If we get 0 over 0, then we can factor and cancel out. But if we get a non-zero over 0, the limit does not exist. The only time we have to go further with this problem is if it's a one-sided limit. Then we have to decide what's happening at 2, whether the graph is going to positive or to negative infinity, since it's approaching a vertical asymptote. But in this case, we're asking for a limit, so therefore it does not exist. Limit as x approaches 0. First thing we do is we plug in our target x value. 0 into the numerator, we get 0. 0 in the denominator, we also get 0. So 0 over 0. So here, we're going to actually multiply by the conjugate of the denominator to help us through this problem. So if I distribute through, I'm going to get x plus 3 minus 3, which is just x. The x's cancel out. We're left with root x plus 3 plus root 3. Plug 0 in for the root x, and we get root 3 plus root 3, which is going to be not root 6. I'm sorry. This should end up giving us 2 root 3. And then 21, limit as x approaches negative 4. First thing we do is we plug in the x here. So negative 8 plus 8 is 0. Negative 4 minus 4 is negative 8. 0 over a non-zero is going to be a real number. This is the real number here is 0, so limit does exist at 0.